Myself Dr. W. Gunule from Kalani Mahavidyalaya, Nagpur. Today I am going to discuss the second part of carbohydrate, in which today we are going to see the structure of glucose, and after that we are going to see the epimerization and mutarotation. And here, as we know, the structure of glucose can be determined, and determination of glucose, structure of glucose consists of different steps, that is detection of element, structural formula, molecular formula, presence of aldehyde group, presence of 5-OH group, straight chain of carbon, and after that the ring or cyclic structure. So by using all these steps, we suggest or we can determine the structure of the glucose. So the second part of this carbohydrate today we are going to discuss, and here, so first part that we are going to see is the structure of the glucose and determination of ring structure of the glucose. And here, as we know, glucose is one of the simple and useful monosaccharides, and determination of the structure of the glucose consists of different steps. So here, first step is a detection of element. As we know, from the qualitative analysis of pure sample of glucose, it found that it consists of 3 elements: carbon, hydrogen and oxygen only. And second step is now structure of glucose. Now here the second step is the molecular formula. Percentage of carbon, hydrogen and oxygen in glucose was calculated from its quantitative analysis, and it is found that it consists of 40% carbon, 6.6% hydrogen and 53.33% oxygen. This suggests the empirical formula CH2O, and molecular weight from the depression in freezing point method is for the glucose is 180. Therefore, the molecular formula is fixed, and that is a CH2O6. So CH2O6 means we can also write C6H12O6. And third step is now presence of 5-OH group. So in glucose, 5 OH groups are present, and this suggests that glucose can be easily acetylated, and on acetylation product, penta-acetyl glucose is formed. This indicates the presence of 5 hydroxy OH groups, and glucose is quite stable and does not lose water molecule easily. This indicates that all the 5 hydroxy groups are attached to 5 different carbon atoms. Oxidation of glucose by periodic acid gives 1 molecule of formaldehyde. This also indicates the presence of 1 primary hydroxy group, that is CH2OH group. So this is the third step, and next step is number 4, presence of aldehyde group. So glucose easily give the addition product with the hydrogen cyanide, and condensation product with hydroxyl amine. All these reactions indicate the presence of carbonyl group. This carbonyl group must be present as aldehyde group, because on oxidation glucose gives carboxylic acid without loss of carbon atom. For example, already we have seen the reaction. On oxidation by bromine water, glucose gives gluconic acid, while oxidation with concentrated nitric acid, glucose gives saccharic acid. So reactions are shown here, the two here. So glucose on oxidation on this oxidation bromine water, it gives gluconic acid, and oxidation of this is give saccharic acid with concentrated nitric acid. So this is the number 4th step, and after this, next step number 5 is a presence of straight chain of carbon atoms. So here in glucose there is a straight chain of carbon atom, and here we can say that on reduction by HI, hydrochloric acid, at 100 degrees Celsius in presence of red phosphorus, glucose first give 2-iodohexane and finally hexane. This shows that all the 6 carbon atoms of glucose must be in a straight chain. So it is shown after the reaction. So it forms first 2-iodohexane, and after that En hexane. So all the carbons are in a straight chain. Glucose on oxidation by periodic acid give one molecule of formaldehyde along with the other products. This indicate the presence of one primary hydroxy group. So this is the number 5, and next step is number 6 is the structural formula of the glucose. As we have seen 5 steps from all the above discussion, we have seen on the basis of first 5 steps, we can conclude that molecular formula of glucose is C6H12O6. Glucose consists of single chain of 6 carbon atom. Glucose also consists of 5 hydroxy groups attached to the separate carbon atom. And number 4, glucose consists of one aldehyde group. The aldehyde group is monovalent and therefore must be present at one end of the carbon chain. Therefore, considering all these points and the valency of carbon and hydrogen and oxygen, the structural formula of glucose is shown here. So this is the structural formula. On the basis of all the above steps, we can write the structural formula. So it can also be written as CH2S, CHOS, CH, CHOS, CHOS, CHO in this way. So this is the structural formula of the glucose. And now next step is the 7th number, configuration of the glucose. The above structural formula as given in a previous slide of the glucose consists of 4 asymmetric carbon atoms. Therefore, there are total 16 optically active isomers and glucose is one of them. All the 16 isomers are known, and there are 8 pairs of enantiomers, that is D and EL form. That is a glucose. These 8 forms are glucose, mannose, allose, ultrose, glucose, idose, galactose, talose. These are the 8 isomers. The configuration of glucose is proved to be, so the configuration of this glucose is shown here. This is the D glucose, positive and negative D and EL are there. So this is the structure, and 4 asymmetric carbon atoms are shown by the star, and glucose is dextrorotatory and have D configuration as it is related to D-glyceraldehyde. This arrangement of hydrogen and OH along a symmetric carbon atom shows that the stepwise synthesis of glucose by Kiliani synthesis. Starting from the D-glyceraldehyde, D-glucose is synthesized by introducing new asymmetric carbon atom one by one. So in the next slide we are going to see how this D-glucose is obtained. So here this is the step by step of the formation of D-glucose. So here this is D-glyceraldehyde. It is now then to this is having, from this we get 2 erythros and 3 O's, and now this D-erythros forming 2 types of ribose, D-ribose and D-arabinose, and this D-arabinose forming 2 types of compound, and what is D-glucose and D-mannose. So D-glucose, step by step we obtain from the glyceraldehyde the D-glucose. So here glucose from here we have seen this is the flow chart, and next step is now last step 8, that is ring or cyclic structure of the glucose. The structure, as we have seen in a previous slide, of glucose is known as a open chain structure, and it shows the presence of free aldehyde group. The open chain structure can explain molecular formula and number of properties of glucose. However, it fails to explain some points. Therefore, there are some drawbacks of the open chain structure. And number 1, that glucose does not restore the pink color of Schiff's reagent and does not react with the ammonia, sodium bisulfite, even though it consists of aldehyde group. Second point is that glucose pentaacetate does not react with the hydroxylamine, showing the absence of aldehyde group. And third point is that glucose exists in 2 stereoisomeric forms, that is alpha and beta glucose, having different specific rotations. Glucose also forms 2 methyl glucosides. And number 5, open chain structure does not explain the mutarotation. So all these are the 5 drawbacks of the open chain structure of glucose. And therefore, to explain this defect, Tollens in 1883 suggested a ring structure for the glucose. He first suggested that 5-membered ring containing 4 carbon and 1 oxygen atom. It is also known as butylene oxide, and later Howarth confirmed the presence of 6-membered ring containing 5 carbon and 1 oxygen atom. It is known as amylene oxide. According to these scientists, there are 2 structures for glucose which differ only in arrangement of hydrogen and hydroxyl groups around the first carbon atom. These 2 forms of the glucose are known as alpha and beta glucose, and they are interconvertible through the open chain structure which is shown in this slide. So this is the alpha glucose and this is the open chain structure, and then they are interconvertible, and here is also beta glucose. The arrangement is different as compared to alpha, and this is beta. So here now here these are the structures, alpha glucose and beta glucose, 2 isomer, and they are interconvertible with each other. So alpha is converted to beta, and beta can be again back converted into the alpha structure, alpha glucose structure. So these are the ring cyclic structure, and after this now we are going to see. So this is the structure. By using all these steps we can determine a ring structure or the different by using different step, or we can suggest open structure of the glucose and also ring structure for the glucose. Now another concept is there, that is known as the epimerization. So what is meant by the epimerization, and what are the examples of this epimerization? So it is observed that aldohexose, that is glucose C6H12O6, can represent 16 optically active isomers. Already we have seen. All of them are known. Out of these, 8 have D configuration and remaining 8 have EL configuration, dextro and levo configuration. These 8 isomers having D configurations are, so here in this slide shown, different dextro isomers, and another negative are there. So D configurations are here: D-allose, D-altose, D-glucose, D-mannose, D-glucose, D-indose, idose, D-galactose and D-talose. So these are the, so here the arrangements are different, hydrogen and hydroxyl groups. So here these are the isomers, and here after that we are going to see the example of this epimerization. So what is epimers? Now here these 8 isomers form 4 pair. Each pair of these isomers differ only in the configuration of carbon adjacent to the aldehyde group, and they can form same oxygen on treatment with the excess of phenylhydrazine. Such aldones which differ only in the arrangement of carbon atom adjacent to the aldehyde group and which can form same oxygen are known as the epimer. And the process of converting the one compound into its epimer is known as epimerization. For example, glucose to mannose, allose to altose, and so on. Epimerization therefore includes inversion of the configuration of carbon atom adjacent to the aldehyde group. The epimers can form same oxygen because only the aldehyde group and adjacent carbon atoms are involved in oxygen formation. The configuration at remaining carbon atoms of both the epimers is identical, and Fischer successfully converted aldose into its epimer. It is shown in the slide, and Fischer shows the method to convert aldose is first oxidized to aldonic acid, and aldonic acid on heating forms gamma lactone by the loss of water molecule. Therefore, aldonic acid is first heated in the presence of pyridine, and it prevents the formation of lactone and convert to the aldonic acid into its epimeric acid. Structure number 3. and forms mixture of 2 and 3. These acids are separated by using the difference in solubilities of the salt of these acids. The epimeric acid 3 is then converted into lactone structure number 4 by heating. Lactone on reduction give the epimer aldose structure number 5. So the change of aldonic acid 2 to 3 take place through the intermediate enol form. So all these steps are shown here in this example of the slide. And so here there is the what is D-glucose first convert by oxidation converted gluconic acid, then by using this pyridine at temperature D-mannonic acid is formed. So this is structure 1, structure 2, structure 3, 4 and last 5 we get. So then gamma lactone and it is converted into the mannose. So in this way, this is the example of epimer, different structures are formed. And lastly we are going to see the mutarotation. So what do you mean by mutarotation? So mutarotation is a typical property shown by majority of the reducing sugars. Only some ketones do not show mutarotation. On standing, a solution of sugar slowly shows the change in its specific rotation and become constant after some time. Such spontaneous change in the specific rotation of the solution of optically active compound is known as the mutarotation. I am again repeating, such spontaneous change in the specific rotation of solution of an optically active compound is known as the mutarotation. For example, we can consider the example, there are two forms of glucose. Alpha glucose is a form which can be obtained by crystallization of glucose from cold ethanol, and melting point is 146 degrees Celsius and the specific rotation is plus 110 degree. Another form is beta glucose. It can obtain by crystallization of glucose through hot pyridine. Its melting point is 148 degree and specific rotation is plus 19.7 degree. In aqueous solution, both the forms show mutarotation. Specific rotation of alpha glucose decreases up to plus 52.56 and that of beta glucose increases up to plus 52.56 degree and remain constant. The process can be catalyzed by heating the aqueous solution alone or with acidic or basic compound. Tollens explained that this mutarotation by suggesting two forms of glucose having furanous structure, and Howard suggested a 6-membered Paranotch ring structure which is supported by X-ray analysis. The two forms of glucose are interconvertible in aqueous solution through the open chain structure. The solution of alpha glucose or beta glucose on standing slowly forms a equilibrium mixture and containing 38% of alpha glucose and 62% beta glucose. The specific rotation of this equilibrium mixture is a 52.56 degree. Therefore, we can say that mutarotation of glucose can be explained due to such interconversion, that is alpha glucose is in equilibrium with the beta glucose. And actually also we know that mannose also shows mutarotation. Specific rotation of alpha mannose is a plus 34, beta mannose is a minus 17 degree, while equilibrium mixture has specific rotation plus 1 by plus 15 degree. So as we know the mutarotation is thus due to the conversion of one form of optically active compound into other forms having different specific rotation. The mutarotation, that is the change in specific rotation, stops when equilibrium mixture of the two forms is formed. Mutarotation requires presence of amphoteric solvent like water. Mutarotation is prevented in acidic solvent or in basic solvent like pyridine, but it is possible in a mixture of pyridine and cresol. The interconversion of one form into other in aqueous solution take place as shown in this slide. So mutarotation in aqueous solution involves opening of ring and reclosing of the ring in the original or internal position. So here is the interconversion of this alpha glucose and beta glucose. So specific rotation of this glucose is 10, here 19.7, but after this when equilibrium is come then it is 52 like that. So here, so two forms are in equilibrium and this is known as the mutarotation. Their specific rotations are in equilibrium. At on standing it acquire, one is increases, other is decreases. So this is the mutarotation found in case of the glucose. So today we have discussed the structure of glucose, and after that we have seen two important concepts, that is epimerization and mutarotation. So we have seen different steps to determine the structure of glucose.